Okay, well, I'm very pleased to welcome Doug today. He's up at Cornell, and his background sort of in the notice that was distributed. He has a strong background in climate modeling, particularly sort of human impacts and other things we're doing. I might say that the early focus on this climate intervention effort was in rather large sensitivity studies. So could you offset a CO2 doubling or even a CO2 quadrupling with it? They were really not very plausible kinds of studies. It was all a sensitivity study to sort of see if you could do it. And then sort of GeoMIP, an intercomparison project, stepped in and sort of standardized a lot of runs, and they've started to run some more realistic scenarios. But over the past couple of years, there's been much more effort trying to look at trying to do something that might actually be plausible in a policy sense. So trying to stabilize the climate and keep it steady, prevent further warming, or maybe take it up a little bit or down. And Doug and his activities have been pretty instrumental in that. And so that's sort of the focus we talked about as for this presentation. So with that, Doug, glad to have you here, and feel free to go forward.
All right, thank you. I see lots, moderate number of faces that I know, and a bunch of people that I don't know or have seen emails from, and now I can put a face to some of the emails as well. I'm gonna talk for a while. There's a bunch of things that I want to say, but by and large, discussion is good. Ask me whatever questions you're interested in. I'm gonna try to keep my remarks mostly fairly high level, so I'm not gonna drill super deeply into any one aspect in particular. So I have a slightly weird background in this space. I was originally a mechanical and aerospace engineer. I was working in industry in the 90s doing program management, primarily feedback control type stuff, dynamics and control. Wound up doing a little bit of work in climate science, and then I met David Keith in about 2004. And he introduced me to this subject. I'm like, well, that's kind of interesting. There was a workshop at NASA Ames in 2006 that I was at that I think was the first US conference specifically about solar geoengineering, although they weren't allowed to use that word. And so Ken Caldera came up with this solar radiation management term to deliberately obfuscate that the meeting was about geoengineering. And then I've basically been working on this a little bit starting then and more or less full-time for at least 10 or 12 years. I don't really care what we call it, solar geoengineering. IPCC calls it solar radiation modification. My personal preference is just to call it sunlight reflection methods. That keeps the IPCC acronym, but I basically just uses plain English, and rather than terms that people don't understand what it means necessarily. And I actually want to start, there's a couple of problematic aspects to this slide, but it's the usual starting point for most people. And certainly people who have not been familiar with the conversation with SRM, there's a sort of a slide that's sort of a useful way to help articulate the position we're in, which is that, of course, we have to cut CO2 emissions to zero. When we get CO2 emissions to zero everywhere on the planet is when, roughly speaking, things stop getting worse. So that doesn't solve the problem. Anybody who says cutting emissions is a solution to climate change, that's the wrong word to use. It's a piece of a solution. You then go say, all right, well, we can solve the problem by pulling the CO2 out of the atmosphere. Lots of ideas for how to do that. Somebody else here probably has a better answer than me on how much of that we're currently doing, but we're off by several orders of magnitude still relative to the scale we need. So I think it's clear to me that eventually we should be able to do that, but it's very unclear to me when we're going to be able to do that and how rapidly we're going to be able to do that. So the critical thing with all of these is that there's huge error bars on them. There's error bars. If I told you the emissions, we don't know how much the planet warms. We have no idea what future policy looks like. Well, we can guess. It's probably going to look anybody who thinks we're going to go zero emissions globally in the next 20 years, I think is probably smoking something. And huge uncertainties on the technology side as well, which would basically put us in a position of saying the future is going to be worse than today. Today already has climate impacts, and we do not have a guaranteed strategy to avoid significant climate change. So, even for the people who find the idea of geoengineering to be distasteful, at a minimum, if you said we shouldn't even be doing research on this topic, I'd say you're gambling with everybody else's future. You're gambling with the idea that if we can cut emissions fast enough and pull CO2 out of the atmosphere, that's going to be good enough. And the reality is, I think we can all hope that it's good enough, but I don't think you can guarantee that. And some of us might have different estimates for that probability, but the probability that that's good enough is clearly not zero. So there's at least 3 problems with this slide. First is that this time axis is potentially long, depending on how much you overshoot and how fast you can pull CO2 out. That time scale could be quite considerable. Second, I sort of drew this, well, first of all, that y-axis, climate impacts for CO2 and mitigation and CDR, you can kind of just scale everything as a proxy, using global mean temperature as a proxy for a whole bag of climate impacts. But we don't really care about global mean temperature. We care about all sorts of other stuff. And solar geoengineering does not cool the planet the same way that CO2 warms it. So you don't get back to the same place. So 0.2 on this diagram is cooler than 0.1, but it's not the same as 0.3. And then 2 other things. First of all, I think there's a number of people on this call would point out that drawing a flat line sort of implicitly at a temperature higher than we're at today is not necessarily the right answer. We already have climate impacts today. That's a design choice, right? If you decide to do some amount of solar geoengineering, you get to decide how much to do, and you get to evolve that over time and maybe decide 20 years in that it's like, no, we actually want the planet cooler, or something like that. The other big issue on this whole thing is if you said, oh, the purpose of research is to decide whether the green line is less risky than the blue line, the implication is that those choices are uncoupled. And I would say the number one concern that people express around the planet is the question of, referred to as moral hazard, right? So if people decide to start doing solar geoengineering, does that lead to a reduction in how much attention you pay to mitigation? My personal view is that that's a pretty small risk. Other people disagree, but that's, if you talk to different people and you get different perspectives on the value of research, that's usually where the sticking point is, whether they explicitly acknowledge that or not. So as a prelude to everything else, I would more or less say I'd be, from a purely physical climate impacts perspective, I would be pretty damn confident that it's less risk to do some amount of geoengineering, some amount of reflecting sunlight than none, provided that you're assuming the same emissions pathway. This is just a picture from the National Academy report, which only looked at atmospheric approaches. So it did not look at space-based, which is probably pretty far out right now. It's more expensive. certainly plausible in the long term, but it's not going to happen in the next 10 or 20 years. And it didn't look at surface-based approaches simply because it's actually really hard to get enough surface area reflecting on the surface of the planet to do something meaningful. So the idea that's best understood, put stuff in the stratosphere, put aerosols in the stratosphere, that's the idea I would talk about the most. And we know that it works. So large volcanic eruptions do this periodically. That's the Mount Pinatubo, which erupted in 1991, cooled the planet by a little less than half a degree Celsius. So I have 100% confidence that if you took a bunch of airplanes and you flew them up to the stratosphere and you released sulfur dioxide, you're going to cool the planet. And actually the existence of that volcanic analog also sort of says, there's some unknown unknowns, but, we at least have some way to calibrate our models. That's just temperature plot from volcanic eruptions. The idea that's next best understood would be, but is much more uncertain, is marine cloud brightening. So those are ship tracks that you see in that satellite picture, interaction between the pollution from the ship and it basically creates clouds or can make clouds brighter. So you see it particularly where there wasn't a cloud and the pollution created a cloud. But even if there are existing clouds, it can make them brighter. You don't need pollution. You do that with sea salt spraying up into the clouds. Cloud, we know for sure that there are lots of conditions where if you add aerosols, the cloud will get brighter. We also know for sure that there are conditions where if you add aerosols to clouds, the opposite happens. You cause the cloud to rain out. I think the boundary between those is not perfectly well understood. So there's sort of a little bit more research needed on that. But I'll say a little bit more about that later. I'm not going to say anything about cirrus cloud thing. I noted Dave Mitchell's on the call, so if there was a question about that, he's probably better suited to answer it than I am. So one slide from modeling. This one's a little bit old, but just scale to illustrate kind of what models show. On the left is the pattern of temperature and precip maps if you allow the planet to warm by a degree with CO2. And on the right is those same maps if you offset that warming with stratospheric aerosols. So you don't get back to exactly where you are. The precip response is not as well compensated as the temperature responses. But this is sort of the argument, it's pretty hard to look at those two maps and not conclude that there's very strong evidence that the maps on the right would be less risk than the maps on the left. That, of course, is not the full story. So what do we know? Stratospheric aerosol injection, at least, is pretty straightforward to do. Cost is somewhere in the billions, doesn't really matter broadly whether it's 5 or 10 or 15 billion. It's basically free relative to the costs of climate change or anything else we do. With a slight caveat, there's probably not very many countries that are actually capable of doing it, contrary to a lot of what you might read. And that's just because you need specialized aircraft to get up high, and the challenge there is getting the engines, and nobody is going to sell you an engine. There's only a couple of countries that make engines. Pratt & Whitney is not going to sell you a jet engine unless the US government at least tacitly approves, for example. We know it would cool, lots of climate impacts get better, right? If you're interested in Arctic sea ice, sea level rise, heat extremes, we know for sure what the sign of the effect is on all of that. Or permafrost loss or Greenland ice sheet loss, for example. Antarctic is a slightly more complicated story. It doesn't simply reverse climate change. I mentioned that there's residual changes in precipitation. They're probably fairly small relative to, they're certainly on average smaller than the changes in precip from climate change. But there may be places in the world that don't care that much about temperature changes and do care about precip changes, and they might object. Outcomes depend on how it's done. It's not just this oh, do we do stratospheric aerosols or not, for example? Depends on where you do it. Same with marine cloud brightening. It depends on where you do it. Other things with stratospheric aerosols, they do affect ozone. Honestly, that's got a lot of press, but it's not obviously a big deal. Acid rain deposition, again, you'll see some press on that relative to what we currently dump into the atmosphere. Relative to our current acid rain issues, you could cool the planet practically back to pre-industrial for about 10% of that. Changes, you don't just reflect sunlight back to space, you change direct diffuse sunlight ratio. The asterisk on the relatively few countries with capability I'll get back to later, but the tropopause, so stratosphere is basically, brief bit of atmospheric physics. Troposphere is heated from the ground. Sunlight is absorbed at the surface, it heats it from the ground, hot air rises, so that's convectively unstable. So if you put pollution into the ground, it's all mixes, gets rained out pretty quickly. High enough up in the atmosphere, you get the tropopause. Above that, it gets warmer with altitude in the stratosphere because UV, the ozone absorbs UV from the sun. And so that's, since it's warmer at the top of the stratosphere than the bottom, that's stable, right? Because hot air rises. If you put stuff in the stratosphere, it lasts for order a year instead of putting it in the troposphere that lasts for order a week. So it's way more effective. That's why it's essentially plausible to put enough material in the stratosphere. But the tropopause is lower at high latitudes. And so it turns out that it's plausibly a lot easier to do this at high latitudes, and that's where there are a lot of climate change impacts that might be of concern. Societal dimension, if you do this, it affects everyone on the planet. How you make those decisions is unclear. My personal view would be, as long as most people on the planet think, oh my gosh, climate change, it's going to be bad. It's not bad now. It's going to be really hard to get support to deploy. If climate change gets to the point that everybody's like, holy crap, this is catastrophic, we have to do something now, my guess is, that situation around the ability to make decisions will be change. I already mentioned the effect on mitigation. Clearly, there's some potential for conflict. If you were deploying it for a really long time and relying on it for cooling and you ever stop, you kind of go back to where you were over 10 or 20 years. It's not instantaneous. And then in terms of research, I think it's still fair to say it's mostly in the developed world. It's mostly climate modeling. And I'd actually say to date, a lot of the research has been curiosity driven rather than mission driven. That's sort of one of the things that I and a few other people are trying to change and say, this is, we need to actually get answers that are relevant to society. What do you, sorry, I haven't been following the chat. Yeah. So what do we need to know from a science perspective? I can sit here and say, look, I've read piles of papers, I've looked at piles of simulation results. I think it'd be less risk if we deployed this. Nobody is going to deploy it based just on Doug saying that. You're going to need some broadly legitimate international assessment report that comprehensively looks at the science before you're likely to get a reasonably legitimate global decision towards deployment. I think that holds regardless of whether you're talking about stratospheric aerosols or marine cloud brightening, with a few caveats in that marine cloud brightening could be done on a much more regional scale. So basically, what do you need to know? Essentially, what do you think would happen to all of the stuff we care about? And how do those answers depend on choices like what latitudes do you put things in on, how much do you cool, and so forth? And then equally critical, how confident are we and what are all the risks? That's not just the physical climate uncertainties, but also, like what is the risk of moral hazard? Is that something we can do research about? And what can we do to reduce those risks? I think I said all the rest of that. But I will also say, to me, coming from engineering, this is, engineering in the true sense of the word of applying scientific principles towards a specific end. This isn't just, oh, let's go put aerosols in the stratosphere in our climate model and see what happens. You go do things like say, all right, what latitudes, what happens if I put them in at this latitude? What happens if I put them in at that latitude? Can I mix and match? Right, there's some design elements to it. There's some specific aspects of how do I go about reducing uncertainty and doing risk management and so forth. So how do we get there? One, Mike, I think, mentioned this. A lot of the research that has been done was just kind of like, oh, this is an interesting idea. I'm going to go take my climate model and put a pile of aerosols in it and see what happens. That's not directly relevant for doing risk comparisons of the sort that you would want to do in like a big IPCC assessment report that says, okay, if we follow this path, here's what the impacts are. If we follow that path that uses some amount of SRM, that's what the impacts would be, right? So you want scenarios that are plausible. You want to repeat those in piles more climate models than we have to date. A lot of this stuff is still done in just a handful of climate models. You want to pass that down to every single climate impact, ideally. And you want to do all of that in a way where the people in the developing world and so forth trust the research. So there's some challenges that need to be careful about the research effort itself. This is just from a paper a few years ago, last year. And this gets at a comment that a few people have actually made as well, which is, so we sort of started as a default, we're going to start deployment roughly when our climate model, roughly when the world would pass 1.5 degrees. 2030, maybe it'll be earlier than 2035, but that was sort of a reasonable estimate. Also look at what happens if you cool further than that, back down to 1 degree or 1/2 degree. If you care about something like Antarctic ice shelf collapse and associated sea level rise, you might want to do that. And also things like what happens if you just delay for 10 years and hold off on a decision. What are the impacts of that? So looking at scenarios that you can more directly compare. The other big thing that we've been working on is looking at the latitudes of deployment. I'll just go to the next slide. So trying to basically say like, okay, and we haven't done all of this work for marine cloud brightening yet, but it's in progress. By piece that by me, by lots of other people as well. But just sort of take a look at all of the different places that you could put aerosols into the stratosphere. They mix longitudinally, so you don't have to worry about that. If you put them in over Ithaca, or you put them in 10 miles north of here, nobody's ever going to be able to tell the difference. So this is sort of like a reasonable set that was sufficiently distinguishable. I'd really say the main things are you could put them in at high latitudes, you could put them in at mid latitudes, you could put them in the tropics. All of those things do a little bit different. If you put them in the tropics, you kind of overcool the tropics and undercool the poles. If you put it in at high latitudes, unsurprisingly, some level, you focus more effort on the poles. So you overcool the poles, if you will, and undercool the tropics. Or you can just think of that as like, where is it that I'm most worried about? There are issues if you put too much forcing in one place versus another. You change, the atmosphere is trying to move heat around. So you can't like just cool the Arctic. If you try to cool the Arctic, the planet will move a lot more heat northward into the Arctic. And if you can change the temperature gradients, and that has impacts on precipitation and so forth. So you have to be a little mindful of all of that. So what do we know? Don't do it in one hemisphere, at least not very much, because that'll shift intertropical convergence zone. I said that. I did not emphasize too much. That's simpler to implement, but you could potentially even start a small deployment with existing aircraft at high latitudes. I'll say a little bit more about implementation later. And then once again, this is from the scenarios on the previous plot. In principle, if you're quote only cooling the planet by a little over a degree, that bit about, oh, it doesn't, you're warming the planet with CO2 and now you're cooling it by a different mechanism that leads to some novel climate. For the most part, most of the surface is actually indistinguishable from the reference climate. That is to say, for the most part, if you view this as a magic undo button, that's actually not that far off for a small amount of cooling in climate models. And then, of course, there's a big question of there are uncertainties in climate models. We can calibrate a little bit with volcanic eruptions, but we don't have observations of what happens if you cool the planet, and so we don't have proof that that's what would actually happen if you were to deploy. This was just a little bit more on the Arctic one. So a couple of papers I've noted here. The one on the top right, which is what that plot is from, that's Walker's results. Basically, injected 60 north. The tropopause is much lower, so it's much easier to get airplanes to do that. We have to have a paper with Wake Smith, who actually looked at that. Kind of do it with existing airplanes, but you're still high enough that if you actually wanted to sustain it, do significant cooling and sustain it, you probably want to design dedicated airplanes to do that. Bottom line is, you want to restore Arctic sea ice, you could. Then the question is, what are all of the rest of the ramifications from that? And then we have a paper that's not yet out, so technically still embargoed, but should be out next week or so, by Paul Goddard at Indiana, looking more carefully at what happens to Antarctic under some of these strategies. A little bit more complicated just because of there's some dynamic effects that the big issue with the Antarctic is you have these floating ice shelves that are holding back all the sea ice, and they're being warmed from the bottom. And the temperature at the bottom of that is influenced by ocean currents as well. And so you need to spend a lot of time paying attention to how does the deployment of stratospheric aerosols, for example, affect ocean currents. I think the bottom line is, yes, as long as you're a little bit more careful about how you do it, you can clearly reduce the risks. We're not at a point of saying, here's exactly how much you would need to do to prevent a tipping point in Antarctic. Implementation, this slide is actually a couple of years old. Wake Smith and some of his colleagues did a really good job sitting down and saying, okay, if you want to do this in the tropics, people have been doing climate model simulations where you put stuff in at 21 kilometers. No airplanes can fly at 21 kilometers with a useful payload. And so they went and did a paper design study and so essentially said, you can go buy airplane engines from GE. Not fundamentally hard to go design the airframe. You could go do it if you wanted. It would probably cost $5 billion in 5-10 years to develop the airplanes. So keep that number in mind a little bit. You cannot just say, oh, we're going to go deploy this tomorrow, because you're limited by this ability to make a decision to deploy. That is limited by not really having an adequate scientific basis to give people sufficient comfort to make that sort of a decision. And you're limited by whatever timescales it takes to develop the engineering hardware you need to deploy. The caveat to that is, again, this high latitude option that you could at least do a little bit at high latitudes with existing aircraft. Probably couldn't get very much cooling with existing aircraft, but you could get a little bit while you were trying to figure out how to ramp that up. I'm not going to talk about marine cloud brightening implementation because there really isn't, I would say there's not yet enough understanding of the details of the cloud aerosol interactions and where you'd want to do things and how much you need to inject and so forth to get a really robust estimate. But, I would say, once again, marine cloud brightening is probably not expensive to implement compared to climate change damages. I think when you're thinking, an important way to think about this in general is that at some level you're weighing what are the impacts and risks of climate change against the impacts and risks of SRM. Lots of us can probably, spend 24 hours giving a talk on that climate change side. On the SRM side, you can sort of think of it as 4 different categories. This is sort of my grouping. The physical effects of a responsible, well-designed deployment is primarily what we've modeled in climate models, that I would essentially say it is extremely high confidence that those risks are themselves less than the risks of climate change. However, you also have to worry about the physical effects of like poorly managed deployment, including what would happen if somebody were to terminate during a deployment. You do have to worry about, is there a real substantial risk of moral hazard or mitigation deterrence or whatever you want to call it? And is there a substantial risk of conflict? Because you know perfectly well, I already get emails all the time from crackpots accusing me of being responsible for every single storm that happens. And by the way, apparently I caused the forest fires in Maui a few months ago. You know perfectly well that if there actually really was a deployment, every weather event on the planet has the potential to be blamed on that deployment. So I think those risks of the human dimension need to be taken seriously. Doesn't mean that that's a showstopper, it just means they need to be taken seriously. Second broad comment about risk. This is the engineer in me doing program management. I'm still involved in 30-meter telescope project that I've been involved with for now 23 years. We have a massive risk registry. Every large engineering project has a massive risk registry where you look at every single uncertainty or risk and you quantify how wrong could we be, or what's the risk of this particular thing happening, and what are the consequences of being wrong. I have seen scientific talks where people are like, oh, in this climate model, ozone goes up by 2 Dobson units, and in this climate model, it goes down by 2 Dobson units, and that's totally uncertain. And the answer is, with a baseline of a couple hundred, plus or minus 2 is irrelevant. Who cares whether, sure, you don't know what the sign of the effect is, but if it's 0, practically 0, it just doesn't matter, right? So there's a way of thinking here that is maybe, I don't want to be too critical of scientists, but sometimes they get like hung up on uncertainties without being careful to quantify them, how important they are. And conversely, when somebody tunes a climate model, they pick a set of parameters, and then they say, okay, with this set of parameters, do we match Pinatubo observations, for example? But they don't then typically say, well, how much can I vary these parameters and still match Pinatubo, right? So how well are my observations constraining it? And then you have one version of the climate model that's been tuned, but you don't have like sort of the only way in some sense that you're looking at uncertainty formally then is by saying, well, NCAR tuned their climate model and here's the answer they got, and the UK people tuned their climate model and here's the answer they got, and they're different. So there's a way that we have not been very systematic about sampling that space and saying, how wrong could we be and what are the consequences of being wrong? The other broad comment I would make about deployment and uncertainty is that I feel like a lot of the discussion globally has this sort of brain mindset of like the decision to deploy is like jumping out of an airplane, right? You have a, somehow you just make this decision and you jump and you can't unjump. That's just not the right way to think about this, right? The way you would actually do this is you do a bunch of modeling. At some point, you may or may not, I don't get to make the decision. Nobody in this room gets to make this decision. At some point, somebody says, well, maybe we should go proceed to the next scale. You then, buy a bunch of Gulfstream aircraft or whatever, and you strip out the seats and put some tanks in and put a bunch of stuff in the stratosphere. Broadly, you can imagine similar steps for something like marine cloud brightening. For stratosphere, you could put in enough that you would sort of follow the aerosol cloud, not enough to affect the climate. And you'd then say, at least does my aerosol cloud match the models? If it doesn't match the models, then you might say, something's wrong. Maybe we should go back. If it does match the models, you say, okay, well, I've got at least some confidence I can start scaling things up, right? And you start, it's not like you're getting to 1 degree cooling overnight. You're gradually ramping things up. That gives you lots of times to check to see whether your models are correct and to potentially adjust your strategy, including to the point of saying, okay, we're going to stop trying to cool the planet. So a lot of the, there's risks that people imagine that are not necessarily actually risks that you would encounter in the real world. I'm not going to say very much about marine cloud brightening. Most of my focus has been on stratospheric aerosols. I'm just going to show one plot here. This was Sarah Doherty at University of Washington sent this to me, showing the observation stratocumulus cloud deck, not the model, but the actual observations, and then highlighting regions where one would expect marine cloud brightening might be effective. And the game plan right now is to sort of follow a little bit of a similar strategy of what we've done with stratospheric aerosols, which is go perturb each of these regions separately, look at what they do to the climate, and say, okay, well, can we combine forcing in different regions in some optimal way that to achieve different objectives? One of the observations, of course, if you looked at what the radiative forcing was with stratospheric aerosols, if you put them in both hemispheres, you can get a pretty uniform distribution of aerosols around the entire planet. And you can get a fairly uniform radiative forcing, and that roughly compensates the radiative forcing from CO2. With marine cloud brightening, you've got a patchy forcing. Yes, the atmosphere moves heat around, but it isn't perfect. You are going to get a more spatially heterogeneous response. That's what models say. That's what basic physics would say. And that's just to say, that's not to say one is better than the other. They're trade-offs, right? Marine cloud brightening is not, it's not going to perturb atmospheric chemistry in the same way. And it doesn't have the same fear factor necessarily. You tell people you're going to put sulfate aerosols over their heads, and they might say, you're nuts, you're out of your mind. You tell people we're going to go spray salt water in remote marine clouds, they'll be like, sure, sounds fine to me. I haven't heard any, Australia has started trying to do this in the marine cloud over the Great Barrier Reef, and I haven't heard a single person say that's a bad idea. But there are trade-offs. If you were truly objectively looking at these things, the climate response part, the shifts in temperature and precipitation, are almost certainly going to be less risk from stratospheric aerosols. Anyway, I think that's sort of the main things that I wanted to highlight at least, and make sure we leave lots of time for discussion and comments and so forth. I can probably find slides on all sorts of different topics. But I would say, just as a more general comment, first time, I think I gave a presentation in about 2000, and, after I went to this NASA Ames meeting in 2006, and I gave some presentation in 2007 saying, hey, the next thing I'm going to go work on is geoengineering. And I didn't get to my conclusion slide. I got yelled down by so many people who were so aghast at the concept that anyone would research this that I couldn't actually even finish my talk. Now, I have every single dean at Cornell, the president of Cornell, the head of the Sustainability Institute of Cornell saying, absolutely, yes, we need to go do this research. Tell me who, can we go hire more faculty in this area? How do we help you raise money to do this? And the situation has changed completely. Other than a handful of people who signed there's a non-use agreement that went out last year. Virtually everybody I talk to is supportive of research, and that's both the developed world and the developing world. If you ask people in the developing world, by and large, the answer is a little bit of skepticism of, the global north has screwed us in the past, they might screw us again, but also, look, we're the ones who are going to die from climate change. If there's a technology that can address climate change, get out of the way. We need to pay attention to it. So you do see a little bit of both of those from the developing world. But personally, I see a lot more of the second than the first. Okay. I did one direct comment to me about this bit about the milky white sky. Yeah. Yes, the sky would be a little whiter. Ben Kravitz and I wrote a paper about that in 2013. If you were doing enough stratospheric aerosols to cool the planet by something like 3 degrees Celsius, you probably still wouldn't notice the effect if you were in a city. But if you were in the countryside, you'd say, when I was a kid, I saw blue skies and they looked just a little bit paler. But I'm sorry, if you're cooling the planet by 3 degrees Celsius, the alternative is probably so catastrophic that it's like, okay, we should accept that. And I think this is also one of these problems with, I was involved in a study back in 2017 where the scenario was stupid. I didn't choose the scenario, but I was involved with it, and it wound up getting used in all sorts of impact assessment. And it involved cooling the planet by 4 degrees Celsius at the end of the century and then they ran the climate model 20 times. So, and then you look at a 20-year period, and you essentially now have 400 years of observations of using stratospheric aerosols to cool the planet, and you say, hey, look, I can see this effect over here. And I'm like, look, if the alternative is a planet 4 degrees warmer, I don't care that we reduce the Indian monsoon strength by 5%, right? So there's been there's a lot of the media coverage has been really problematic, and that's been partly driven by well-intentioned but poorly represented science that has been more focused on, hey, I want to understand some detail, rather than, hey, I want to convey an appropriate information specifically for policy. Termination shock risk. That's a damn good question. Nobody knows. If you were using this to cool the planet by 0.5 degree, you warm back up by 0.5 degree over the next 20 years. That's not that different from our current rate of warming. If you're using this to cool by 2 degrees and you turn it off, that could be pretty bad. So that, then is asks it. So, there's two questions there, right? What's the impact if there was a termination? And what's the probability of a termination? And how do you then design governance and design, if you're deploying stratospheric aerosols, don't do them out of one airbase. Don't have a single supplier for your aircraft. Don't have a single country deploying it. Maybe that's okay if you're doing 0.2 of a degree cooling, but if you're going to do a degree of cooling, don't do those things, and you can reduce the risks of ever having a geoengineering.
Doug,
yeah.
Here, Doug, let me sort of what we've done in the past is I'll try and call on people on questions if they'll raise their hands or something like that. So we don't have to do it.
Sorry.
I'll read it, but no, that's okay. And so I want to take one prerogative and sort of ask the first question, even though I have a dozen. But the notion of that we would get there with an IPCC assessment sort of bothers me, because IPCC basically says its mission is to just report on what's in the literature rather than to drive a process of trying to really understand something enough to make a decision. And so I guess I'm sort of curious if we should be starting to think about some other kind of process for doing that, some mission-directed process. I don't disagree that we need a nice scientific recommendation, but if all IPCC does is sort of report on what's in the literature and there's no effort to drive the literature by governments, will we ever really get to anything? So should what the assessment process is or how that process works be something we talk about?
So yes, and let me say two things. First of all, I think in principle, you're right, but I think you can solve those two things separately, right? So you can say, we are going to go do mission-driven research, and there's several efforts I'm involved with right now to actually fund that and write down a clear roadmap and execute according to that roadmap. And then if you do that, you will have the literature that you can then use to assess. The second thing, of course, is who's going to do that assessment. Right now, of course, there's a cadre of senior lead authors in the IPCC that are a little bit of the over my dead body, to the point of I've had conversations with one that was essentially willing to lie.
So one of the other problems,
and explicitly, because of the view, this absolute concern that if we allow this out to be mentioned, if we allow the public to find out about this, it's going to detract from mitigation, and so we're going to lie to the public.
Yeah,
that's the viewpoint that I've had from at least one person. So we have to change that too.
One aspect also of the IPCC is it's driven by the scientific decision-making process, which says I want findings of high confidence before I come to a conclusion, as opposed to the relative risk kind of framing that one might want to use in an existential problem. So it really seems to me that we need to come up with a different way of thinking about how you get to a decision here and proposal or something like that. So, okay. Let's see.
I think you're absolutely, we need relative risk, not, and which is why I would put a big emphasis on the research on, uncertainties and risk and not just on.
Yeah, I mean, I think
it should be comparative.
One of the failures has been not having sort of a risk kind of assessment in the summary for policymakers instead of having scientists be able.
Well, and that's where I would like. I quickly looked at Michael Mann's response to Jim Hansen, and I was like, totally, no offense to Michael Mann, but I'm completely appalled that he essentially ignored the entire concept of uncertainty. He basically said, I have my estimate, and my estimate is correct. Yeah. No acknowledgement that no, actually, you're at, the correct way to convey stuff is to say, here's my guess based on this, but it might be wrong. And as soon as you say it might be wrong, we don't need to get into an argument of whether Jim Hansen is correct, estimate is correct, or Michael Mann's is correct. If it's even possible that Jim Hansen's is correct, we need to be doing something.
Yeah.
If it's even we don't have to argue whether like AMOC shutdown is 5% likely or 90% likely, right? If it's 5% likely, you got to do something.
Okay, let's go to the questions. Let's see. In my lineup, Jonathan Cole was first. Jonathan.
Hey, thank you. That was a really great presentation. Um, I want to pitch the idea that you include a slide about ground-based reflection because I build prototypes of foil reflection devices, and I've shown them to hundreds of people, and only one or two in all those hundreds have actually understood the idea that photons move in straight lines, and that if you reflect something back out to space and nothing, it doesn't bump into anything on the way out, it goes all the way out and that energy has gone with it. The level of understanding in the public, even within science circles that are not climate science, is so low in terms of the basic physics of cooling through radiative adjustment that the benefit of promoting the ground-based stuff, even though it's maybe slow to deploy and maybe it does take thousands or millions of kilometers to do it, the benefit is that when I give people these devices to take home, they play with them, the kids shine them in each other's eyes, and they get the real tangible sense of how the cooling occurs and how much energy there is in sunlight. So I would just make that pitch that you include a little more about the ground-based reflection, because if it does roll out across the farmland, even 10% of the farmland or something like that, you can get a very big effect on it, as well as cooling the plants and stuff.
The biggest effect you would actually get is if you like cool buildings so that you reduce your air conditioning demand, so that you reduce fossil fuels. So roughly speaking, to get all the way back to pre-industrial from where we are today would be a little less than 1% sunlight that you need to reflect. But 1% is a hell of a lot of area, right? So, the advantage of stratospheric aerosols, the reason that that's sort of plausible is because you're getting that area with lots of tiny things, so that you don't have a lot of volume. The advantage of marine cloud brightening is there's a hell of a lot of ocean, and you're just using the clouds. The problem with doing it on the surface is simply like the continental US is 2% of the world's surface area. So if you want to reflect enough to get a significant cooling, you're talking like a reasonable fraction of the continental US, and that's just a lot of area. So that's the reason that I haven't talked about it. Combined with, you do get from a climate response perspective, if you're putting all your forcing in small places, if you tried to actually scale it, you would actually be changing climate.
Right. And
my answer one time was that what you need is a styrofoam continent floating on the Pacific. But okay, let's
you can manage outgoing long wave a little bit too. Manage the city.
Let me go to Robert Hula.
Yeah, look, that was just awesome, Doug. Thanks so much. A couple of things I wanted to raise. First, the issue of urgency that you flagged in the AMOC context. Just the fragility of Earth systems seems such that with Arctic melt and various other tipping elements that we really need to move quickly on this. But I wanted to just refer to this chart from your paper from last year, showing that with SAI, with I think 20 million tons a year, roughly, it would be possible to get back below 0.05. And then just to take one example of abundant examples of the problem is a paper coming out in Nature just this week, just saying that looking at this carbon budget concept in order to stay below 1.5 and completely ignoring the question of albedo and the ability of albedo to keep us below 1.5. And then finally, there is some level of opposition to the MCB trial in Australia. This is a paper from Friends of the Earth. And so a couple of things there. Thank you.
Thank you for pointing me on that last one. for all people's angst, you constantly get this angst about, oh, we can't possibly do anything outdoors. And it's like, well, where's the opposition? But yeah, thank you for pointing me on that. Yeah, no, you constantly see stuff saying, this climate impact is unavoidable, this climate impact is unavoidable. And none of them say, well, you could avoid it. It's just.
Okay, let's see. Peter, do you want to?
Yeah. So Doug, wonderful presentation. Are you going to be providing the slides to us?
I certainly can if you want them.
Yeah, they're very good. I haven't really studied this for almost 10 years, and it's progressed phenomenally. One point and a question. The Mount Pinatubo, I have a new paper out that's not looking for a place to publish. I can send it on the list here, about the Pinatubo pause, that in addition to the cooling in 92, there was also, we had net zero that year of CO2. That CO2 levels were stable. They were going up 1.5 parts per million per year, went to zero in 92, and then in 93 went back 1.5 parts per million per year. The point there being that I think getting CO2 back to, assuming that we are willing and interested in learning how that happened, probably, which is probably ocean fertilization, iron fertilization, then we may be able to replicate what happened in CO2. And then if you do that, then the termination shock becomes much less of an issue because you don't need to do 2 or 3 degrees.
Right.
And yeah. And so just for everyone who knows me, I never talk publicly about SAI, about SRM, because of that reason, saying as soon as we talk about restoring CO2 levels, then it becomes a total no-brainer. Anyway, that's my comment. My question is, in terms of getting social license for doing it, we've put together our Climate Restoration Safety and Governance Board, which could cover, and I probably will eventually cover SAI, but have you thought about what mechanisms to use for getting social license?
I certainly know people who've thought about it. I think my broad reaction would be that the fundamental precursor to that is a sufficient body of legitimate, trusted science, and that, me putting, here's a plot from one climate model conducted by one group on one scenario with one tuning of the parameters in the climate model, I doubt that people will base their acceptance on that. Although I still think the reality is that social license is going to be driven far more by what happens with climate change than any research we do on geoengineering.
Great.
But I don't think that situation is going to change overnight, but it's hard. I can't predict the future on that. There's lots of efforts to at least, do a better job of communicating. And then my reaction is do a better job of being clear on the research, doing simulations that are not 4 degrees of cooling, but are sort of more policy relevant, and doing a better job on the risk comparative framing, and not just saying, oh, look, stratospheric aerosols would affect this, or marine cloud brightening would affect that. Right?
Yeah, that's great. Can we schedule a little offline chat about social license?
Yeah,
great.
Absolutely.
Great, thanks, Doug. Fantastic job. Can't wait to have the slides.
All right, thanks. Ron?
Thank you, Mike. I think Herb was before me, but that's okay.
I'm sorry.
Yeah, go into Herb. Yeah.
His hand is up on a yellow wall, and I couldn't see it. Okay.
Yeah.
Go ahead, Ron.
Zoom sorts them for
Be
you.
a little shorter than you usually are.
Okay, Herb, go ahead.
Oh, you want me? All right. Well, again, like everyone else, Doug, it's just I thought it was the perfect combination of technical enough to get across important and detailed concepts and not always intuitive ones, and very accessible. And I hope you find the time to give this to many people in many different places, you and your colleagues. That said, a couple of just quick comments. One is I rebel when I even hear serious discussion of moral hazard. To me, even discussing moral hazard is a moral hazard. I think of it as cooling deterrence rather than mitigation deterrence. But I only just want to make that comment. But I don't know which of our lists you're on, but we've had some discussion about that in the last couple of days. But I think that what surprised me was what sounded like you were fairly sanguine about opposition or support for cooling, particularly from the global South and so forth. And while you're immersed in it every day, and I'm not, but it's been my experience, it's been just the opposite. The indigenous community, the contacts I've had with them, they just see it as completely. I don't want to overgeneralize, but the folks we've talked to see it as completely incompatible with their worldview. Social justice advocates, people like Greta Thunberg, are vehemently against it. And of course, as you pointed out, the IPCC authors that are willing to lie, which is not the first time I've heard a similar anecdote to that. And even the White House, when the report that Congress had them do, that they released at the end of June, they sort of had this off the record hot potato, like, okay, we had to do this report, which is a report basically outlining a research agenda. But we want to make it very clear anonymously, we're not supportive of this, we're not going to fund it, et cetera, which I took from the fact that there's no lobby basically making them be more open to it. The only people they hear are the opponents of cooling. So if you could just both respond to that and also just maybe briefly, even though it's a broader question, if you were the sort of philosopher king, if you will, of the planet, what would be kind of an ideal pathway to get from here to deployment, if warranted, past all of these political and governmental and institutional obstacles? I know that's a lot to ask, so you can pick and choose which you want to respond to.
How many hours do you have?
Exactly. Yeah. I don't. We want to make sure Ron and Robert have enough time.
I'd say there's a huge amount to unpack there. On moral hazard, the reason that I mention it is that if you want to understand why people are opposed to geoengineering, I think you have to recognize and call out that is actually the source of their concern, right? So why would you be strongly concerned about termination shock? Only if you thought that you were using this as a substitute, right? As Peter points out, right? If you do get emissions down and you manage to pull CO2 out of the atmosphere, you're not necessarily talking about cutting, cooling by a whole lot. So if why are you concerned about termination shock is primarily because your mindset is thinking that this is a substitute. So it's not always explicit in people's minds, but sort of the Michael Manns of the world, and the IPCC people, lead author person that will go nameless, that's basically the source of their concern. Personally, I think it's nonsense. I think it's so obviously not the situation. If one gets to the point of actually deploying this stuff, I think it's pretty blindingly obvious to everybody on the planet that that's not where we wanted to be. Right? We didn't want to be in a position where it's like, cool, now we can keep emitting. Nobody says, great, I'm going to keep smoking because chemotherapy has been invented, or I'm going to run this red light because I've got airbags. To me, it's just total nonsense as an argument, and the argument itself is morally problematic because if you really parse it, it comes across a little bit like, if you don't watch enough poor people in Bangladesh dying, you're not going to cut your emissions. So personally, I have a big problem with the moral hazard argument but I acknowledge that that's why people have concern. So what do I think needs to happen is we need to change the narrative. And I think it is changing. I don't know. I'm not sure I answered all your questions.
Well, I would just say the other reason, of course, is that now renewable energies are becoming less expensive than fossil, and it's not like anybody's going to go back to fossil. I mean, they might hold on to it a little bit because of their assets, but they're not going. Nobody's going to go back to the fossils given the dropping price of renewables. At least in my view. Okay, Ron.
Yeah.
Now you're
just in terms of that changing the narrative, my view basically is good science will help, but it's not sufficient. So good science and good communication. And right now that's really hard to do when there's like zero money and nobody really pushing for it. But as soon as, there are several groups that are likely to start ramping up research funding. And I think as part of that, recognizing that one needs to do a better job of articulating things is going to come along with that. Sorry.
Okay, Ron.
Thank you, Mike, and thank you, Doug. That was excellent. It's just very refreshing. We've had numerous people presenting to HPAC, and I think we're as I believe we're a community that believes very strongly in the urgent need for cooling, and I think you're sort of been the closest to that view as far as I can tell. And on that note, the urgency, experimentation, and deployment. So I think, we have, I agree with you, we have seemed to have crossed a threshold where most of the community, as far as I can tell, believes in the importance of research. The problem is, we had David Keith, for example, and he said, well, probably about 10 more years of research. I mean, it was a video like this, so I wouldn't pin him on that. It was kind of in conversation, but and part of that was a skepticism about tipping points that if we cross 1.5, that's just kind of a political target. It's not going to be that bad. And to the contrary, I think I believe, and I think many of us believe that is a very serious risk that we need to consider, and we don't really have 10 more years of research. So on that note, and I get the sense that you're sort of at least thinking in this way. Don't we need to do actual testing? I mean, and I proposed sort of a space station analogy, start in the poles, drawing on your work and Mike, who had a paper early on to the White House office on the same topic, that just start very small steps in the poles. You can even frame it as a Great Barrier Reef kind of thing. We want to cool the poles and then try and get the native people and the countries that have some authority in the poles, jurisdiction, to just say, let's just do a little bit. We'll just start experimenting, because I don't see, if we don't start actual experiments, real test deployments, it will take 10 years. I mean, I to be honest, I think I and many of us were quite despairing after we heard from David that this is just, we need more urgency in the community, and it doesn't seem to be on the agenda right now. So anything you could say to that would be appreciated. Thank you.
Okay. Three things. So first of all, with regards to tipping points, my reaction is that there is certainly, in some cases, overhype about one particular study without sort of balanced look at all sorts of things. But my bottom line is this is risk. So I don't need 100% confidence in the probability of a tipping point to act. And I think you can, the correct argument to somebody to say, if David Keith says, I don't believe in tipping points, the correct argument really is much more about probabilities and risk, right? You don't have to convince them that it's 100% probability. You have to convince them that it's not zero, and that it's not a trivial number. with regards to timeline, my guess is I'd be very surprised if any form of SRM is deployed at any reasonable scale in the next decade. That, quite frankly, even if we had the social license today and all the science today, it'd take years. But how much research do you need it's risk, right? For me, I'd say, sure, if I was in charge of the world, I got to make all of the decisions, I might say, I've made my risk calculus. I think we should start putting a little bit of aerosols into the stratosphere, but that's not my decision, and it shouldn't be my decision. So how much research do you need is need for what? Need for whom, right? Exactly what you said, effectively, right? It's a risk calculation. In terms of experiments, my answer is what for? I don't think we should be doing stuff just to be seen to be doing stuff. I think you do stuff with a purpose. So marine cloud brightening, I think we should start doing experiments in about 2013, 2014, as proposed by Tom Ackerman and others, to actually do controlled perturbation experiments of marine cloud brightening. I think it's absolutely blindingly nonsense that those weren't started 10 years ago. Because we don't understand some of the processes well enough to constrain them. For stratospheric aerosols, if you said, let's say we're going to go buy 3 Gulfstream aircraft and put 50 tons, 100 tons, 100,000 tons of aerosols into the stratosphere, I think that's something that you would do as a prelude to deployment, right? You're going to put 100,000 tons in before you put 1 million tons in. But I'm not quite sure that I couldn't argue that that's going to change the answer. I think if you think about it from an uncertainty perspective, a large uncertainty that you need to reduce is one where some realizations of that uncertainty you would choose to deploy and others you don't. Right now, I would not be in a position to say, we have to do this experiment in order to reduce uncertainties. Part of that is because most of the uncertainties that people are really worried about aren't things that you would ever find out about with a small release. But, in principle, I'm open to making doing that more quantitatively and saying, okay, here's exactly what you could learn with this amount of aerosols at this point in time and so forth. But in terms of actually putting enough in to actually start cooling the planet, I don't, right this instance, I would say, sure, my personal view is I think that would reduce physical risks, but I think it would increase societal risks, and I think it would actually slow down stuff in the long term, right? If somebody was pushing too hard for deployment, there's going to be a backlash. So, in some sense, this is all weighing non-commensurate types of risks that none of us know anything about.
So, Doug, I know you have to leave around 5 or something, but there are a couple of questions still on. If you can stay as long as you can, we're happy, but if you have to leave, let us know.
Probably about 5:02 is as late as I could push it and get to daycare before it closes.
Oh, okay, all right. Robert,
maybe 5:03 if I hurry out the door.
Okay, all right. Well, we'll go Robert Christopher.
I'll try and keep my question really short. You glossed across one quite interesting point rather quickly for me, which was when you talked about conflict as being one of the possible impediments, but you then said it didn't need to be a showstopper. Now, I find this whole issue, there's a whole range of things that one could put in that caption or underneath the caption, conflicts. But one of the things that has always exercised me about solar radiation management is the fact that because you're doing it in the global commons, and there's no way that you can control the cross-boundary impacts, the opportunities for any nation or any community to say, hey, look, we've just had a flood, we've just had a drought. It's entirely due to your experiment or your stratospheric aerosol injections. You need to compensate us. Now, one of the things that concerns me is the extent to which our conservative, with a small c, politicians and the legal advisors upon whom they rely for any form of treaty or legislation are going to look at the potential exposure from these sorts of claims, whether spurious or otherwise, and kind of really struggle to approve any kind of activity in this area?
Yes. I think if you wanted to imagine a deployment that was going to be successful, right? And successful means, if you're actually trying to reduce climate risks, you're actually deploying at some reasonable amount of scale for some period of time. If you want to actually do that, there's got to be reasonable consensus. And there may, in order to get that reasonable consensus, you may need to, and might be morally appropriate, to put some sort of compensation scheme in place, right? So that the direct costs of deployment might be completely irrelevant, because the real costs of deployment are, we're going to put a compensation fund in place for people who view themselves to have been damaged by this, right? So that's an active area of research as well. But it's also why I would tend to say, look, lots of us might look at the risks and say, oh, we see big risks. But by and large, most people on the planet do not currently see climate change as a risk. Certainly not a sufficiently existential risk to justify action. Right? So, if you suddenly said, whoops, there's research that convincingly shows that if you're above 1.5 degrees for more than a decade, we're going to get 10 meters of sea level rise or something, maybe that might change the conversation. And if I have to jump off before I get to everybody's question, feel free to email me.
Yeah, right. I was going to sort of ask that and stress that may be necessary. Maybe Greg and Victor, could you perhaps both ask your questions and then see if he has still time to do it?
Yeah, sure. Well, my question is, well, I have a million questions, but I'll just say, when in the modeling, the introduction of the aerosols is fairly blunt. I mean, in a real system, it would be a control loop with different. Yep. It would be, like a real control system, and I think. Yep.
That's me. I am a controls person. I teach controls.
Yeah, yeah. So, to the extent you can manage these the problems that we've talked about of the non-uniformity, et cetera, would be ameliorated by a real control system. Anyway, that's the thing I'd make.
Yes, that's the short answer. The long answer is an hour.
Okay. Well, I might email you.
Yeah.
Victor,
but that's basically what I do. Victor, do you have a quick?
I had some technical question, but if you're in a hurry, I can let you go.
Ask it, and I can always give a very short answer if I can.
Okay. Well, I've been wondering why it's more difficult to deploy SRM in the high latitudes. I realize it's a bit
easier.
It's a bit lower, but
it's easier to deploy in high latitudes because the tropopause is lower.
But
so you don't have to get the airplanes up the top. Mm-hmm.
Don't you still have to get to the stratosphere? So you still have to have like the purpose-built aircraft and.
That's basically Wake's analysis, is that you still, if you want to do it with any reasonable cost effectiveness at scale, you'll need purpose-built aircraft. But now they only need to get to, you don't want to, like, here's the tropopause, right, is not like a paper-thin boundary, and you don't want to be right above it, because the reason is you want lifetimes. You want to be some distance above it, which pushes you, I don't know, we haven't been comprehensive about this, whether you need like 13 kilometers or 15 kilometers. But by the time you say, I want to be at something like 13 to 15 kilometers with a payload, you can go do it with existing KC-135s, but they're all at the end of their service life for fatigue reasons. So you fly them 10 cycles a day for a year, and they're all going to break.
But you only
you basically need to build new airplanes anyway. But it's a heck of a lot easier where the air is denser. You don't need as much wing area. You don't need as much, and your engines flame out at high altitude if you're not careful.
Don't you just need the injection time though to last a few months? I mean, during the peak summer season, and that's all. So,
Spring. You want to put them in like March, April, May.
well, yeah, once the snow starts to melt, there's no purpose doing it before the snow starts to melt, really. Because you're going to be darker than maybe not. I guess it's in the stratosphere, but
It's in the stratosphere, and in actual fact, you get your predominant cooling not over the regions where there's snow. Actually, you get your predominant cooling from being having forcings like south of that, and therefore reducing the heat transport into the Arctic.
oh, okay.
But regardless, yeah, you want to put them in like spring or something like that, so that they're there during the summer, during the peak of the insolation, through the fall. But yeah, no, you still need to get them to altitude.
Okay, thank you
yeah,
very much. I better head out. I don't want your children stuck somewhere.
Yeah. All right. Thanks all.
Thank you very much.
Can't